So today I'm going to talk about one of the latest things we have been paying attention to and focusing on, and that is building data applications with Shiny. I realize a lot of the folks who are attending the meetup are from academic background, graduate students or undergraduate students, or the meetup is being hosted by USC and there are folks from UCLA. So I'll try to give as much context as I can from the enterprise side. I think it would be pretty interesting to know that these days R has a kind of an important role in industry as well as academia. So kind of an obligatory intro slide for my employer who's sponsoring my time here. I work at this company named Databricks, and the mission of the company is building or offering a unified analytics platform that would accelerate innovation by enabling data engineers, data scientists, and analysts all working in the same framework. So they will collaborate with each other much, much easier. So, and often the data scientist is using R, and data engineer wants to use Python, and the analyst wants to use Tableau, and they end up getting siloed with different tools, and it becomes very challenging and difficult to collaborate and work with each other and share data. But we solve that problem by supporting all of these diverse languages and use cases in a single framework. So we're a fairly large startup when it comes to startups. We have several thousand customers. This number on the slide might already be outdated, and we have many partners. And Tableau, which John mentioned, is going to have a training, is like one of our partners. And we have developed several successful open source projects. You've probably heard of Apache Spark. This was the original open source project that the founders of Databricks did, and that's they started Databricks after they developed Spark. We also introduced a new open source project called Delta Lake, and a more recent one called MLflow. In this talk, I'm going to touch on both Apache Spark and Delta Lake. So a little bit about data apps in the industry. Kind of show of hands, how many people here have used or do use Shiny? Okay, so there are a couple of people, like more than a couple of people, and majority haven't used Shiny. Shiny is basically a very popular package, probably the most popular package for building data apps. So what is a data app? You might be familiar with BI tools for building dashboards, and BI tools are very common and very talked about in industry. All enterprises and the vendors focus on BI tools because they have a very large addressable market and they're more manageable. The reason is, with a BI tool, you're interacting with the data through SQL, which is a declarative language, and there are many opportunities for optimization and data management when your data interface is declarative and simple like SQL. However, when you talk to data scientists and R users at various enterprise companies, they prefer to build their dashboards by writing code rather than like dragging and dropping widgets in a BI tool. There are many reasons for it. They mentioned the fact that they want to be able to access data in any way they wish. They don't want to be restricted to SQL. They want to be able to use third-party packages. They want to run a regression analysis or ElasticNet and random forest. A lot of these things aren't as accessible in BI tools. When you're writing code, you can have non-trivial data manipulation. You can massage your data in any way you wish. And when you write code to build a dashboard, you have much more control over the layout and the placement and ultimate details. You can even use CSS to style things. And finally, as a data scientist, when you're doing data analysis, doing the exploration phase, you're building some plots, you're like, summarizing data in various ways. And with things like Shiny, it's very natural and easy to just take your existing analysis and making it a dashboard. So the transition from the EDA to presentation is natural with something like Shiny. And all of these make Shiny the most popular framework for building data applications among data scientists and our users. By the way, if there are any questions, please stop me, and ask your question. I want to keep it interactive. So now here comes the challenge. Bigger companies all have big data, and their data is growing pretty fast. This is very common quote when I talk to data teams or data scientists at various companies, is our data grew beyond our initial assumptions. It grows exponentially. And it's a good thing if you can handle it and manage it, because there's a lot of potential value in your data. So the more you have of it, the better. But at the same time, you have to deal with the challenges. So that's the size of the data that is growing. Big data also has other aspects. The qualities of your data also change with big data. Your data schema changes. There are additional or new streams of data every once in a while. You have to incorporate them. They come from different sources. Their dimensions of your data can change. And the use cases of the data grow and change as well. So, one day you're the only consumer of this table, and the next day a new team or a new person joins the existing team, and now you're doing multiple other uses of the same data. So even if all of these are easy, you constantly look for additional metadata to join and merge with your existing data to increase the value you get from it. Like if you have location data, you want to join it with county level boundaries and produce better maps and things of that nature. So all of these make handling large data pretty challenging. And those challenges all apply to people who build Shiny applications, especially people who, after building these Shiny applications, share them with the rest of their organization, with other stakeholders within the company to consume their apps. So as a result, there's this very, very common architecture. It's a two-step architecture, two-stage architecture for building Shiny apps. The first step is, and by the way, this is this is pretty common in companies where there is large data. When you don't have large data, you may not need to go through this. But the first step is running an ETL job, or like a nightly job, to extract data from your data lake or data warehouse and stage it into an intermediate location. And you usually perform either filtering or aggregation or sampling on the data from this large data warehouse or data lake to make it accessible or manageable by your single node R process and Shiny application. And then the second stage is you basically read from the disk or read from that local, the MySQL database or any other database, and you present it or analyze it in your Shiny app. This is very common. It has some nice things, and it also has some challenges. The nice thing about it is that if you already have a Shiny app, you don't need to make much changes to it. Previously you were reading some static CSV files. Now you're reading new CSV files that are being updated nightly by that ETL job. Okay. Now the challenge is that now you have two data pipelines to maintain and manage. Both of them can have problems. If you change one, the other one might need to be updated as well. In some cases, that staging environment doesn't scale. So all of a sudden your data grows tenfold, and the 1% sampling that you were doing before and was producing 10 megabyte of data is now producing 100 megabyte of data, and your application runs into problems. Also, this is very common at companies that I talk to. The data governance or IT security might not be happy with this staging solution. one common pattern is they were doing everything in an on-prem data center, and they were happy with the two-stage solution, but now they're migrating to the cloud, and all of a sudden, it's not okay anymore to stage intermediate data in a MySQL database in the cloud because it's not in an air-gap data center anymore. So they can't do it. So we at the Databricks have been working with many data teams to streamline and unify their data pipeline using what we call the lakehouse pattern. So what is the lakehouse? The lakehouse is what we call the best of both worlds. You get the nice things or all the nice features from data warehouses, but you can directly operate on very low cost storage for data lakes. So the nice features you want, you get that are available to data warehouses and databases are asset transactionality, schema enforcement, good data governance, decoupling. But the nice things you get from the data lake is like you decouple from your storage. The compute and storage are decoupled. You basically don't need to maintain 100 machines running all the time in order to process the data. You only launch those machines or get those machines when you have a job to run. And when you shut down those machines, your data that is sitting on your cold storage is fine.
Can I ask a question?
Definitely.
If you have your data in data lakes, how are you getting asset and schema enforcement?
Yeah, that is exactly the secret sauce of this project called Delta Lake.
Okay.
Basically, with you don't get asset with Spark on DBFS or S3 or a blob storage, and there's this new component or project called Delta Lake that basically is a data, like at a very, very simple high level terms, is the storage component that you plug into the architecture, and all of a sudden you can get asset transactionality with your Spark jobs. Same with schema enforcement. So you can actually specify guarantees, and if data that comes in doesn't comply, it'll be put aside in like a temporary location, and you'll be warned that, okay, I received some data that doesn't comply.
I have one question. Normally, especially in company, the data is very confidential. So we cannot save the data, for example, like the lakehouse or outside the company warehouse. We only can use, for example, on our laptop. For example, if I use my data on my laptop, can I continue use your programming?
That's a kind of a bigger and much, and a good question. There is no single answer to it, so it depends on a lot of things. I'm going to do a demo, and I'll show you basically no data. In the demo, I'll show you how you can use R and Shiny, and your data wouldn't ever leave the environments of your company. So data confidentiality is actually great in that regard.
Thank you.
Yeah. Any other questions? Cool. So there's support for many types of storage formats. You can have very diverse types of data. For example, you can store images and process images, audio files, semi-structured JSON data. And there is support for end-to-end streaming. Basically, you can have streaming jobs that are constantly dumping data into your data lake. And you can have support for very diverse types of workloads. One example of it is going to be like workloads from R applications. So there's a little bit of a background about this. About 10 years ago, so data warehouses are pretty old. Like they have existed for more than 30 years, and they were great. So companies found that managing data is actually difficult, so they built these sophisticated systems called the data warehouse that would take control of the data. And we're talking about analytics use cases where you're mostly concerned about like running a query or like aggregating and summarizing data for analytics purposes. So these data warehouses would manage data. You would buy a big machine, from IBM or from Oracle, from Microsoft, and that has a proprietary software on it, and it has its own storage. You send your data to this appliance, and then you can ask questions about your data using SQL, and they would offer transactionality, and they would scale up very well. And there were distributed versions of these which were very expensive. The problem was, as data grew and the amount of data grew, these became really, really expensive and became really hard to scale them. So the new pattern came along called data lake. And the data lake was basically introduced with the whole Hadoop innovation in the industry. And people were saying, okay, we don't need to actually put everything into a data warehouse. We put a massive distributed storage like HDFS or blob storage, and we just dump all the data into this lake. And when it comes to analyzing it, then we can just process the data. The problem with data lake is that it then loses on those nice features that your data warehouses were offering you. You don't get as much data governance. You don't get as much transactionality. You don't have schema enforcement. A lot of the nice things you had are now not accessible to you anymore. So now companies are having trouble using the data that they were putting into their data lakes. So the project Delta Lake, along with Apache Spark, together can offer all the nice things that you like about your data warehouse on the data that you've already stored in your data lake. So that's basically the power of this new architecture. And I'm gonna be specifically showing an example of it from the perspective of an R user. So how does this shiny lake house look like? Here I have data, bits fitting into a data lake, in this case, Delta Lake. And I have a Spark cluster. A Spark cluster is a number of machines. One of them is the master node or the driver node. And there are many workers or worker machines. And Spark is implemented in Scala, which is a JVM language. So basically these are running inside the JVM. And I also have an R process running on the master node of my Spark cluster. And I use either SparkR or SparkR to program the Spark cluster. And Spark, along with Delta Lake, would enable me to query massive amounts of data very conveniently. Any questions about Delta Lake or Apache Spark? Okay.
Sorry, Hussein. Can I ask a small question if you don't mind?
Please.
Hello. Hello.
Yeah, I hear you.
Yeah, Hussein, I have also heard about Apache Kafka. So is it similar to Apache Spark when processing streaming data?
Yeah, there's some similarities. Kafka specializes on streams. And they're not exactly the same things. They don't address the same needs, but you can use Kafka from Spark. So Spark is a computation engine. And Kafka is basically a streaming framework. You can do some computation in Kafka using its own variant of SQL. And you can also do streaming with Spark. So there's some overlap there, but by and large, they're targeting different use cases.
Thank you so much.
Cool. Okay, so now let me talk about SparkR and SparkR. These are two different packages, very similar. They were developed to program Apache Spark for R users. So if you're an R user and you want to talk to Spark, you don't need to go and learn Scala or Python. You can do it from R or using either of these two packages. They basically provide an API front end or basically wrappers for Spark APIs. And they expose the Spark data frame concept. So Spark has this thing called data frames, which are basically tables. And the idea is basically stolen from R. When we were adding data frames to Spark, we were looking at R as a model example. So that's how it came to Spark. And both packages, SparkR and SparkR, provide convenient interoperability between the R data frame data structure and Spark's data frame data structure. So with these two packages, you get kind of the nice things that Spark offers, which is a distributed, robust distributed, based by robust I mean fault tolerant distributed processing engine that can load data from many sources and can offer in-memory computation. And you get the very nice things that R offers to you. You have a dynamic environment, it's very interactive, and you have access to a very large packages ecosystem, and you can visualize your results and basically all those things that you like about R. So you get both of them. So without any more high-level discussions, let me show you an example of a Shiny application and show you how easy it is to use the Delta Lakehouse. Basically, it might seem very complex, but it's actually very easy to use. So here in this example, and I'm going to show you a simple demo as well. Here in this example, I'm basically importing the Shiny package, and I'm also importing the SparkR package, and then start the SparkR session. That basically connects my R process to the Spark cluster. And after that, I can write my Shiny dashboard or app. And here, notice that in my Shiny app, I am calling a SparkR function called read.df. And I specify the source of my data being Delta, because I'm going to be reading a Delta table. And I give it the path to that Delta data set. And that's it. Now I have access to a SparkR data frame. And SparkR data frames kind of mimic the APIs of our data frame. So for example, in this case, I'm calling n row on my data frame, and it returns to me the number of rows in that data set. Now, it seems very simple, and it's supposed to be, but under the hood, what is actually happening is when I call n row on my data frame, the Spark workers will actually go to the storage, they will load all the data, and they'll count the number of records in a distributed fashion. So, if I have a cluster with 100 workers, each of those workers is going to load the fraction of the data and count it. And then they're going to send those partial counts to the Spark master, and then the master is going to add them up and then return the result to my application inside the R process. So as a result, I could count the number of rows of petabytes of data within seconds, which is very impressive and kind of impossible without distributed computing. So any questions about this simple toy example?
So what would be a typical latency on a petabyte type data set? I know it depends on the size of the cluster and stuff like that. Because usually Shiny apps are quite interactive, and Spark is not generally quite interactive.
Yep. So that's a great question. And that's why using Delta here is the key. If you didn't use Delta, if I didn't use Delta, I would be dealing with much longer interaction times. But with Delta, it's much shorter because it stores a lot of metadata about data sets. So it performs some optimizations that, again, are common with data warehouses, like data skipping, predicate pushdown, Z order, and that kind of indexing. So you can actually perform, introduce an index based on some of your columns. And if you know that you're going to be querying based on those columns a lot, and improve the latency of your Spark queries dramatically, so that it actually fits within the interactivity tolerance range of your user. So I'm going to show you an example like in a demo. So let me exit full screen here. So do you guys see my the Databricks workspace?
Yes.
All right. So here I have a notebook, and I'm attached to a cluster called Shiny Demo. Let me show you the list of clusters. I have a number of clusters running. I created one cluster called Shiny Demo. It has 16 workers and one master, and it's running this version of our runtime. And these are the instance types, and I created it. So pretty simple way of launching clusters very interactively. It's super easy. I just click here and then create a cluster. But anyway, I don't want to take time doing that. So I wrote a simple notebook If it's not readable, I can zoom in. Please tell me whether I need to zoom in or not.
Can you make it a little bit bigger?
Okay, sure. Is it better now?
Yeah, yeah.
Cool. So here I'm importing the SparkR package and creating my R session. So here it just tells me to import it and some of the functions are being shadowed. Next thing I'm doing is just, what I showed you, read df and, load the flights data set. It's not the biggest data set, but it's pretty common to demo, interaction with large data for R with the flights data set. So, basically I am dealing with 1.2 billion rows. And it took me 3.5 seconds to count them. So that goes to the question of like, how long does it take to count them? In this case, because I'm using Delta, it's much, it's really fast to count the records, because for each partition of my data, Delta is keeping statistics. So it actually doesn't need to count each partition. It just summarizes the statistics on the partitions. So now if I wanted to explore this data as a data scientist, I would, I import my favorite package. We're just talking in the breakout session. What is your favorite package? Reader and ggplot, both are some of my favorite packages. And here I am basically filtering all the flights between SFO and JFK, and I'm grouping by year and the carrier, the airline, and I'm just counting. So a simple aggregation. And here, this is the plot that I get to have. This is the the number of flights over time, and you can see the effect of 9/11 here. There's a dip in the number of flights. So that's pretty cool, except that if I were to explore every pair of cities, this would take forever, and I will need to write code for every pair of cities. Also, I can't easily share this with my colleagues. I want to give them access to this. So what am I going to do? Well, first of all, let me see how many pairs there are. Okay. So here's another aggregation and filtering. So I'm counting all the pairs of sources and destinations and filtering the ones that have more than 100,000 flights, and there are about 2,800 of such pairs of airports. So that's a lot. So I'm going to build a Shiny app for that. And this is the simple UI for my Shiny app. There's nothing special here. I'm importing Shiny and building like the simplest UI that has, an input selector for the origin airport and one for the destination airport. In order to help me pick the names of these, I'm presenting everything in a data table. Now I write my server function, and in the server function is where I am going to first populate the data table. Next, I'm going to generate a plot, and that plot is going to use the input source and destination cities, and then perform that aggregation and count. So over time and by the airline, how many flights do we have between that pair? So filter and aggregation. And then I'm just going to generate a plot based on that data. So let's define the server function. Now all I do is just put them together in a Shiny application. So here is my Shiny application. So I started it. It tells me that my app is going to be accessible at this URL. And I click on it. And here's my Shiny app. So you can see that I have a table of everything. Let me pick a source city, SFO, and destination city, LAX. And now my application is running a query and producing the plot to me. And you can see it's fairly interactive. Within seconds, I get the plot that I was looking for. And I can change it to, let's say, Las Vegas. I want to see if Las Vegas flights did they get affected by 9/11? Doesn't seem they got affected as much by 9/11 as like the flights between SFO and LAX did. So that's a simple Shiny application that is directly accessing my data without having to go through an intermediate stage. Now what I can do is I can take this URL and send it to my colleagues, and they can play around with this data and it's running on the cluster directly, and it's accessing and manipulating the data.
Can you tell us a little bit more about that, the stability of that URL that it's generated? Is it just getting updated every time I decide to run it in my notebook, or
Yes.
does that generate a new URL, or does it update the same URL?
Yep, great questions. Yeah, so this URL, well, it has two components. One is the cluster that I'm running this notebook on, and the other one is the port that was picked by my notebook for this URL. So any of those two can change. So if I want to fix this URL before I share it, one thing I got to do is like in my Shiny app, specify the port number. And that will fix the port part. The second part is I want to make sure that the cluster that I am running this on is going to be stable. So for example, I want to make sure that cluster doesn't automatically terminate, because there is a feature on Databricks that would kill your cluster or shut down your cluster if no one is using it. Or I want to make sure there is proper access control on that cluster so it doesn't get terminated by someone who doesn't have permission to do that. So there's a number of considerations for that. And then I would have a stable Shiny app.
Great, thank you.
You're welcome.
So you're saying that cluster is running the, if you don't terminate it, it's running the whole time, and you're hosting your Shiny app there, and the code would not be checked into some version control?
You don't need to. You can check it in. There is, integration with Git. You can check that code in, but because you're writing it in a Databricks notebook, it's persisted for you, and you can come back to it anytime you want, even if your cluster has terminated. You can share that notebook with other people, and they can like clone it, and they can do anything they want. They can run it on a different cluster. So you don't need to. That part is kind of managed by the software that is running in the cloud.
So another question, as data come in, like when we manage data for Shiny, maybe there's a daily update and it's only available after 8 a.m., things like that. Since this is hosted all the time on the cluster, so that wouldn't be possible, right? It's available as people get access to it.
Let me make sure I understand the question. So your data is updating all the time, right?
Mm-hmm.
And now, what is the concern?
Oh, so before you mentioned the workflow, which is the workflow I use, I put data in a staging area and make it available to just the Shiny app. But using this workflow, there's no such thing as staging area. So your data will be available as it's streaming in, as it come in.
Yep,
The Shiny app will have access to that. So,
yep.
Okay. So
Every
just
time,
I understand.
every time someone accesses the Shiny app or changes the inputs, it would basically hit the raw data directly on Delta and get the latest data. So exactly. So that's why transactionality matters, because your data is being streamed in, it could be streamed in using Kafka or something else, is being streamed in and persisted and saved into your data lake. And you don't need to do anything to get the latest data. Just use it.
I have a quick question. With regard to Databricks, are there tools or features available within the platform to help you diagnose if your Shiny app is maybe running slow? An example would be if you changed an input and it takes a while to query. I just was curious if there's any features or functionality within the platform to help you kind of to identify maybe what could be the cause.
Yeah. There are some ways to debug and find out what's going on. So here I can look at the Spark UI, and the Spark UI is like the most powerful tool to dig deep into what is going on in your Spark cluster. What's the timeline of events? What let's look at this job, and I can look at I can go look at the executors. Oh, this one is not available anymore. This one. And I can look at the list of executors. It's loading. and I can see how much data was provided to each executor, how long it took. I can order them by, let's see, just order them by the amount of data that they got. Some executors got 0 bytes, some got like 40 megabytes of data. And I can see which ones failed, which ones took longer, and so on. So there's a number of ways to debug your Spark application. There's also, this Shiny app is also gonna like maybe run into problems or like have issues, or you can send debug messages. So you can look at the driver logs, and in those, anything you print in your Shiny app code, here, standard out can like basically see what your Shiny, whatever you printed in your Shiny application. So I'm not doing any debugging messages here, but that's another way of debugging. And then there are other tools for like, so the inefficiencies can come from Spark, which is the distributed data engine, or it can come from your R process. And you can like first find out which one is the bottleneck. And then when you find out what is the bottleneck, you can use tools for that to investigate further. So if it's in Spark, you can use the Spark UI or other tools, Ganglia and other tools to look at your cluster. If it's inside your R process, you can use any of the packages for, there's a package by, very famous package by RStudio for debugging performance issues. I forget its name. Yeah, so you're free to use those packages.
Thank you so
much.
One
other thing I would say is, one other thing is sometimes you want to debug interactively. Some people find it much easier to debug their Shiny app using RStudio. So here we have kind of RStudio running on this cluster. I can log in, and this is, and basically run my Shiny app interactively here just for debugging purposes, or like while I'm developing it, and then optimize it and tune it and play around with various aspects of it. And then when I am comfortable, then take that code and then run it in a notebook and then share it with other people.
Hi, I have one question. Just use the Shiny app to get a result. I noticed actually the create dashboard is in the URL. So that means, for example, if I create a dashboard, I want to share with my customer, this customer, remote customer. So he has no data, he has no any idea about R programming. So I want to share the dashboard. This one they can explore. For example, how many year, which year in 2020 they has how many increase or something. So if I use this programming, just create dashboard in URL, how can I share with my customer?
So let me make sure I understand the question. You wrote your Shiny app and you just want to share that URL with your customer, right?
Your dashboard with the customer, yeah.
Yeah. Well, that customer, that user needs to have access to your Databricks workspace. So they need to log into Databricks, and they need to also have permission to run queries against that cluster. So there are two steps that they need to, the two conditions they need to satisfy. First, have be able to authenticate to, be able to authenticate the Databricks. And second, be authorized to run queries on that cluster.
The issue is that they maybe have the database, but he has no any idea. For example, how to run the R, run this the programming something. Because for example, I have created a dashboard already. So for example, I just wish the customer can use for example, the filter, you just use the picture, the Las Vegas is kind of information. He want to explore like this way, but he has no clue how to run this R programming.
Yeah, that's the whole point of Shiny, right? You're not asking your users to run any code; they just play around with these widgets and they get their results. Like that's the problem Shiny solves.
I just noticed you create the dashboard is on the URL. So the URL, for example, I create this one dashboard on my desktop. The dashboard only can be shown on my desktop, but it cannot show my customer desktop.
Yep, absolutely. This is only possible because I'm doing it inside the cloud.
Okay.
Yeah.
Okay, I got it. Thank you.
Cool. So let me a little bit about that. Basically, this is a great segue into what we are dealing with. This is all running inside the cloud, and there's a lot of machinery in place that enables this. We have a cloud service that is interacting with AWS or Azure, or more recently we announced Google Cloud support. That is, when I launch a cluster, goes and starts instances and configures them and makes them secure, and gives them access to your data. And then we have this data engine or distributed data engine, which is comprised of Spark and Delta Lake. Both of them are like open source projects. You can download them and use them on your laptop, or you can download them and install them on your on-prem cluster. But we take care of like configuring them and tuning them and making sure they work with each other. And we think we're very good at it because we wrote them. And then finally, I'm using R and Shiny inside this notebook, which is the data science workspace. So it's very convenient to like import them. They're already pre-installed. Just with the one command, I get my cluster configuration up and running, and with one line of code, I start talking to it from my R notebooks, and I can also do it from R Studio. So there's a lot that's going on, and all of that is kind of possible because there's a lot of engineering that has been done behind the scenes to offer that notebook experience, and that's basically what we do. That's what we have been working on